Hi, welcome back to Lesson 3 in Unit 7 of Algebra 2. This unit is all about imaginary numbers and the larger set that includes both imaginary and real numbers we call the complex numbers. We're going to be finishing this rather short unit today with this Lesson 3. We'll start with a bit of a review of some of our number operations, and then we'll look at just a little bit more application of imaginary numbers. So what I'd like you to do is practice 3.1, which has A, B, C, D, E, and F. And then we'll go over your answers. All right, so hopefully by now you've paused the video and completed those problems. Let's take a look. Okay, so this here we'll simply multiply using our FOIL. 6 plus 9i minus 2i minus 3i squared. But we remember that I squared is actually a negative 1, so that makes us a plus 3, making this 9 plus 7i. Here we need to square this number, and we're going to use the fact that a plus b squared is equal to a squared plus 2ab plus b squared. So that makes this 4 minus 2 times a negative I. 2 times negative I is negative 2i, but times by 2 is negative 4i. Then plus I squared, which is actually a negative 1, making this 3 minus 4i. When we divide, we have to multiply the top and bottom of the fraction by the conjugate of the denominator, which gives me 15 minus 5i minus 6i plus 2i squared over 9 minus 3i plus 3i minus I squared. Those will always cancel out, and I squared is negative 1, so minus a negative 1 is actually a plus 1. So this gives us, let's see here, that becomes a minus 2. This gives me 13 minus 11i all over 10. And you can divide each term by 10 if you like, or just leave it like that since it doesn't reduce any. On this problem here, I'm going to simply multiply it by 2i on top and bottom. You could also multiply by negative 2i, but you don't have to, so I won't. So I get 14i minus 16i squared over 4i squared, which becomes 14i plus 16 over negative 4. And I'm going to rewrite this with the real component in front, and I'll divide. So I get negative 4, that's 16 over negative 4, and then minus 7 over 2i. I could also have left it in this kind of reversed order, but we just usually prefer it. Maybe you thought to just reduce everything by 2, and so you wrote 8 plus 7i over negative 2, or something like that. Or maybe even negative 8 minus 7i over positive 2, depending on how you multiplied. The absolute value is best visualized by graphing. 1, 2, 3, 4, negative 3i is right here. The distance from 0 is the absolute value. This is a length of 4, and this is a length of 3. This is our 3, 4, 5 Pythagorean triple. 3 squared plus 4 squared, square rooted, is 9 plus 16 is the square root of 25. So the answer is 5. On F, we simply just need to distribute the minus and collect like terms, giving me a 4 minus 3i. All right, next I want you to practice 3.2. A, B, C, and then that's it. Solve over the domain of complex numbers. I'm not saying that all the questions have imaginary roots, but if they do, express them. All right, let's see how you did. First, I set it equal to 0 by subtracting 5x and adding 1. I'll then use the quadratic formula because this will not factor. 8 plus or minus the square root of b squared, 8 squared is 64, minus 4 times 1 times 3, all over 2 times 1. Well, 64 minus 12 is going to be a positive number, so this is going to have some real solutions. So I need to find the square root of 52. Now 52 is 26 times 2, which is 2 times 13. So you see I got a pair of 2's. So this is 8 plus or minus. I bring out the 1, 2 for the pair, and I leave the 13 inside, all over 2. And I can divide each one of these numbers by 2, so I will. 4 plus root 13, 4 minus root 13 are our solutions. Let's try the next one. 2x minus 2x squared plus 3 when I distribute, and then I have a minus x plus 1 on the other side. Again, I'm going to get this equation, all the x's on one side here. I'll add x, give me 3x, and I'll subtract 1, giving me plus 2 is equal to 0. The next thing I think I'm going to do is divide through by a negative 1, because I don't like having a negative in front of my x squared. I just don't. And if I have an equation, I can do that. Now, it would change the shape of the graph, but it keeps the zeros the same. All right, this is factorable, actually, so I'm going to factor it. Because that's going to be a minus 2 and a plus 1. That gives me a negative 4x plus 1, and it says negative 3x. So 2x plus 1 equals 0, and x minus 2 equals 0. I get x equals a negative 1/2, and x equals a positive 2. All right, let's try the next one. Distribute a negative gives you negative 2x squared minus x is equal to x plus 5. I'm going to add over here, so I have the 0 on the left. Give me a positive 2x squared plus 2x plus 5. This is not factorable. X equals opposite b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So that becomes a 4 minus, that looks like minus 40. So 4 minus 40 is a negative 36. So this is going to have an I in it. Now 36 is a perfect square, so I can just say the square root of 36 is 6, and because of the negative, I have an I. And I'll just reduce every one of these numbers by 2. So negative 1 plus or minus 3i over 2. So those are my solutions, my complex imaginary roots. Okay. One of the most important skills that an Algebra 2 student learns is how to construct a quadratic equation from the zeros. We've seen how to do it with rational zeros, irrational zeros, and now we're going to look at it with imaginary zeros. Suppose I have a quadratic function with zeros of negative 3i and positive 3i, and the equation contains the point 120. So I can construct this quadratic function by remembering that x minus the 0 is a factor. This is not a rational factor or a real factor, so it's a little bit unusual. But still, we know that that's the case. If I plugged in negative 3i for x, this would become 0, and it doesn't matter what this is, because if this factor is 0, 0 times anything is 0. But don't forget there's also an a, right? We're doing y equals a times x minus the first 0, x minus the second 0, if you like to have formulas, but I just think of the factors. So we don't know this a value, but we know the rest of this is correct. Before plugging in the 120, though, let's multiply out these factors and see what happens. X squared minus 3ix plus 3ix minus 9i squared. The I squared becomes a negative 1, making this a plus 9. And notice that these terms went away. And after multiplying the two zeros, we should always get a quadratic function that does not have irrational or imaginary coefficients. Now, I simply need to find out what a is. I'll plug in 1 for x and 20 for y. 1 squared is 1. So this is 20 is equal to 10 times a, so a equals 2. So y is equal to 2 times x squared plus 9. All right, let's take a look at another one. On this problem, we were told the leading coefficient is negative 1. That means a. That makes the problem easier, doesn't it? Because we can just say negative 1, and then our zeros are x minus 2 minus I and x minus 2 plus I. And I went ahead and put the parentheses to do it right, but you'll notice that it ends up being just minus the 2, and then one of these is plus and one of them is minus. So distributing the minus to both ends up just not really making that big a difference. Now let's expand this. Now remember I told you we shouldn't have any i's when we're done if we do it right. So x goes to x squared. Then x goes to minus 2, minus 2x. Then x goes to minus ix. All right, now we're on the negative 2. Negative 2 goes to x. Negative 2 goes to negative 2, give me a 4. Negative 2 goes to negative I get plus 2i. Now we have the I. Plus ix minus 2i minus I squared. All right, we know that I squared is a negative 1, so minus I squared is actually a plus 1. Plus 2i minus 2i minus ix plus ix. And now we see that we're left with a negative 1 times x squared minus 4x plus 5. Distributing the negative 1 gives me negative x squared plus 4x minus 5. This is a quadratic equation that has zeros of 2 minus I and 2 plus I. I would really commend you to check that by using the quadratic formula and seeing that that's exactly what you get. All right, just by way of review, remember we can do the same process with irrational zeros. These are real zeros. They would be located on the x-axis, where the x-intercepts are of the parabola, but they are not rational numbers because of the square root of 2. I don't know the a, but I know the factors are x minus 5 plus root 2, if I distribute the negative here, and x minus 5 minus root 2. So 1 plus, 1 minus, but each time a minus 5. Now I'll expand this out. X squared minus 5x minus x root 2. Then I'll do the negative 5. Negative 5x plus 25 plus 5 root 2. Now I'll do the root 2 plus x root 2 minus 5 root 2. And minus root 2 times root 2 is 2. Okay, goes away with that one. That one goes away with that one. And I get x squared minus 10x plus 23. But I still have that pesky little a. Let's plug in 2 for x and negative 7 for y. 2 squared is 4. 2 times 10 is 20. So that becomes 27 minus 20 is 7. So negative 7 equals a times 7. So a is equal to negative 1. So our equation is y equals negative x squared minus 10x plus 23. All right, we got just a few more problems to do here. I want you to use the discriminant to determine which of the following functions have imaginary zeros, but we don't need to find them. Remember, in the quadratic formula, the discriminant is the part under the radical. If that part under the radical is positive, we know we're going to get 2 real solutions. If it's 0, we only get 1 real solution. And if it's negative, we're getting imaginary solutions. So b squared minus 4ac tells me if these zeros are real or imaginary. Since this is a negative number, I have 2 imaginary zeros. And this technique of using the discriminant to classify different equations carries on well beyond Algebra 2. This pops up in calculus, advanced calculus, differential equations, all sorts of stuff. Lots of applications beyond just simple quadratic functions. So it's an important skill for you to learn. All right, let's try the next one. B squared minus 4ac. So 9 minus 8 is 1. So this one does not have any imaginary solutions. You can say 2 real or maybe no imaginary, because that's what we're asking, is what has imaginary solutions. All right, let's take a look at this one. 12 squared minus 4 times 9. That's 144 minus 4 times 4 is 16, and 16 times 9, 54, 144. So that's 0. So it actually has 1 real solution. No imaginary. All right. I have a few more practice problems for you to do. I'm going to ask that you do these on your own. and we're just going to stop there for today. So give those a try, and good luck.